Welcome to another edition of Late Night Mathematics. I'm your host, Ted Z. I've been on the lookout for really cool applications of the extended sine law. If you don't know what that is, see the playlist that I have on the extended sine law. I will put a link to it in the description box. It's like the sine law, but a lot more powerful. And what do I mean by more powerful? Well, in order to demonstrate that, we need to look at some cool applications of the extended sine law. And I have found like the best one so far. And that is Brocard's point. Take any triangle and put a point P inside. Now that we have P inside, draw these segments that go from P to A. Let me get my pen back. P to A and PB. And then P to C. So draw these three segments. And we can move P around a little bit. We can jiggle it around. And why don't we try to do something interesting? Let's see if we can make these angles equal. There, I used some color. It should be possible to move P around until these three angles are equal, and I get something like this. Here I have placed P in exactly the right location, so I have these three angles equal x, x, and x. P is called the Brocard point. More precisely, it's called the first Brocard point. What is the second Brocard point? Well, to learn what that is, you have to get to the end of the video. I will tell you near the end. And x is the Brocard angle, so our job will be to find this x. Now, we haven't really proved that P exists for every triangle. We can do that by a geometrical construction. And that could be the subject for a future video. That's a very interesting topic also. But today I'm going to solve for x. We are going to find a formula for the first Brocard angle x, and we will leave the question of its uniqueness. It is unique. We will leave that to a future video. There are many formulas for the Brocard angle x. The one that I want to derive today is the following. This one. And indeed, this is the formula that I used to make these figures in the first place. This one has a proof that relies on the extended sine law. Now, the proof is complex. It has many steps, lots of trigonometry, lots of geometry, but the proof is beautiful and logical, and it has a very nice symmetry to the whole thing. I wouldn't show you something that's really ugly, and I mean, why make a video on that? It's a gorgeous proof with beautiful steps. It's just a lot of work, so be patient, and let's get to it. Since we're going to use the sine law and extended sine law many times in this video, we had better review what these things are. Here's a triangle with a typical triangle labeling scheme. Vertices are A, B, C. The sides are little a, little b, little c, and like usual, they are opposite to the vertex. And I call the angles alpha, beta, gamma corresponding to ABC. Right, so the typical usual sine law looks like this. That is the sine law we know and love from school. A over sine alpha is b, little b over sine beta, and so on. But the question remains, what are these things actually equal to? They are equal to each other, but they are equal to what? And that gives us the extended sine law. So if I draw a circle through points A, B, C, through my vertices of my triangle, and the radius of this circle, if I call that r, the diameter is 2r, well, I get the extended sine law now. It turns out that each one of these terms is equal to the diameter of this circumscribing circle. And like I said before, see the playlist in the description box for a proof of this, plus some elementary applications. And speaking of applications, we need to do an application of our own now. we will use the extended sine law to find a formula for the area of this triangle, area ABC. I use square brackets to denote the area. Now, there are many ways to find the area of a triangle. We want to do it here in a very special way. I want the area in terms of only big R, the radius of the circle going through ABC, and the angles alpha, beta, gamma, so no sides. That's interesting. Have you ever seen a formula for triangle area like this? Well, let's derive it. So I'll mark one of these angles as special. I can choose any one of them. I'll choose gamma. And so immediately we get the area as 1/2 AB sine gamma. Why is that true? Well, it's like the vector cross product. So I take this vector, cross it with this vector. Okay, well, I'll do it in the right direction. And it becomes 2 times the area, yes? Okay, and the cross product is AB sine gamma. Well, I take 1/2 of that to get the area of the triangle. You can remember it that way. Okay, the 2 sides and the enclosed angle, okay, 1/2 of that, and there's your area. Now, it's important to kind of remember this, you know, off the top of your head all the time, because we're going to use it very much in this video. Now we can use the extended sine law to eliminate the sides AB. So from the extended sine law, I have A over sine alpha is 2R, and that gives me what? That gives me A is 2R sine alpha. But I also have B over sine beta is 2R, and that gives me B is 2R sine beta. So, okay, I can take these things and plug them into here, and what do I get? Well, I get this expression, and I have sine alpha, sine beta, sine gamma. I can simplify it a little bit, and I get this. That's a beautiful formula. Area of a triangle without the sides, just the angles and the circle radius that goes through the 3 points. So this is our first important result. You have to remember this formula because we will need this. It's a key element in the proof of the derivation of that formula for Brocard's angle. Now let's look at the angles around the Brocard point, P. What do I mean by that? Well, there's P, and I want to find these 3 angles here, this, this, and this. And luckily, they are not hard to find. Let's start by examining this subtriangle here. So we will look at the corresponding angle over here. That's triangle PBA and angle APB. So what is this angle APB? Well, this angle here is beta minus x. So now I can add these things up, and they have to add up to pi. This must be true, but the x's cancel out, and I get angle BPA is pi minus beta. Oh, that's very nice. Okay, so let me erase this, and I have pi minus beta here. Very nice. So I can color this in yellow. Next, let's do a green one. Triangle PCA and angle APC, that's this angle here. I apply the same idea. This here is alpha minus x. Now I add up all my angles. They add up to pi. The x's cancel out, luckily, and I'm left with APC is pi minus alpha. I can color that in green. Let me write that here, pi minus alpha. So I have one more to do, this one here. This is triangle PBC. I can give it a color. What color should I use? How about red? Okay. So I'm looking for the angle over here, which is angle BPC over here. I add up all the angles. I should get pi. Yeah, I do, and I can solve for BPC. Angle BPC is pi minus gamma, like so. Let me color that in red. There we go. So that was actually pretty easy. I was able to find all 3 of these angles around point P. We have the angles around P. Now let's find the segments around P. Let's label these segments M1, M2, and M3. So M1 is PA, M2 is P to B, and M3 is P to C. Our strategy, our kind of guiding principle is to find M1, M2, M3 in terms of the radius R and the angles alpha, beta, gamma, and x. So it's a similar strategy to that area calculation we did earlier. How are we going to achieve this? By using sine law and extended sine law. Let's start with this subtriangle here. Green is better because pi minus gamma, gamma green. Well, I can apply the sine law to this subtriangle. M3 divided by sine x, that should be equal to a divided by sine pi minus gamma, a typical application of the sine law. So for this green triangle, I will color code all my triangles. Let's do the calculation for this green triangle. We get this, but sine pi minus gamma, that's just sine gamma. So I can now solve for M3. Very good. And we need to eliminate this a, but we can do that by applying the extended sine law to the big triangle. So for the big triangle, I get a over sine alpha is 2r. Well, I can eliminate a now. And there we have it, M3 in terms of only angles and r. Next, let's look at triangle APC. APC, I'll color that in red. This angle here is pi minus alpha. So now I can apply sine laws in the same way. Straightforward application of the sine law, nothing clever, gives me this. And remember, sine pi minus theta is sine theta. I repeatedly use this. I can solve for M1 now. M1 is b sine x over sine alpha. I have to eliminate this b here, but I can do that with the big triangle, triangle ABC, using extended sine law. B over sine beta is 2r. Okay, I can get rid of b now. I get this beautiful formula highlighted in red. Notice the way the angles are getting permuted around. It's so cool. All right, one more. Let's do this one. And I have to give this an angle. This is pi minus beta. We solved for that before. So this is triangle APB. All right, let's try to remember that. I can apply the sine law again, same way. Nothing too clever, just direct application of sine law. I get this, and again, sine pi minus beta is just sine beta, so I can solve for M2. M2 is c sine x over sine beta. Let's eliminate this c. I don't want this c. I can eliminate it using extended sine law. C over sine gamma is 2r. That's good enough. That gets rid of the c. Well, there you have it. Absolutely beautiful formulas, set of formulas for M1, M2, M3, the segments, all in terms of only angles and big R. Now let's compute the areas of those three subtriangles. We use the strategy, the same strategy as before, only in terms of big R and the angles. And how are we going to do that? Well, we have the right kind of formulas for M1, M2, and M3 that will allow us to do that. Here are my three subtriangles with my M1, M2, M3. Now let's write down all the things we proved before that we will need for this calculation. So here are my formulas for the segments M1, M2, M3, and here are a bunch of solutions I found for ABC in terms of angles and R using extended sine law. It's really easy. I've done it many times already. So you no doubt recognize these formulas immediately. All right, let's find the area of triangle APB. I'll color code that blue over here, this one. Well, I can use that kind of cross product area rule. So it's 1/2 M1 here times C, and the angle in between them is X, so that's sine x. And what I need to do here is eliminate m1 and eliminate c. So I'll use this formula here and this formula here. Well, if I multiply all that stuff out and collect all the factors, move them around a bit, I get this. I get a sine squared because I have a sine x here and I got a sine x over here. So I have two of them, so that's a sine squared x. And I'm done for this area because everything is in terms of just angles and the big R. All right, let's try another one. BPC, okay, that's yellow. That's this one here. Cross product area rule gives us this. And now I eliminate the M2 and eliminate the A. So I use this and I use this one here. I get the same kind of beautiful formula with the angles permuted around a bit. Let me color code them. There, I got one more triangle to do. This one, APC, and I will do it in red. Again, using the cross product style rule for area, M3 times B times sine X and 1/2 of all that. Now I must find a way to eliminate M3 and B. I can use M3 formula here and then use the B formula here. And that's the area of our last subtriangle color-coded. Very beautiful the way these alpha, beta, gammas are permuted. It's just totally amazing formulas. All right, we need these three formulas because right about now we are ready to put everything together. Let's recall the area formula that we proved near the beginning. You remember this formula. Let's call that formula number 1. But we also have the following. The area of the big triangle is the sum of the areas of the little triangles. So that's the sum of APB area, which is blue, and BPC area, which is in yellow here, and APC, which is in this reddish color. I can call that formula 2. Well, it's kind of obvious what to do now. Let's just combine formulas 1 and 2. So on the left-hand side, I'm going to get 1 here, like this, and the rest is really hard to write, so you have to bear with me. Okay, we computed this already before, we computed this before, we have all of those areas done in the previous part, so I'm just going to write them all out. We get this absolute beast of a trigonometry expression. But don't lose hope. Things are coming together very well. So what do we do next? Well, let's divide both sides by this whole left-hand side. Right, okay, so if I divide the left-hand side by the left-hand side, I just get 1. All right, like this. And equals what now? Well, all the 2r squares go away, of course. And I'm going to get rid of the sine beta and sine gamma, but I'm going to have another sine alpha in the denominator. And so I get this, and the same sort of thing happens for the other two terms. And there we go. Now we have it. We just rearranged things a little bit. And there it is, a formula for Brocard's angle in terms of the other three angles. Amazing and beautiful. I think the symmetry and the harmony and all of these beautiful formulas, the way the theme is repeated over with eliminating the sides to get just in terms of angles and R, big R. It's just amazing, just beautiful. One of the best trigonometry problems I've ever seen. But we're not done yet. There's still one more thing left to discuss. I said at the beginning that P is actually Brocard's first point here. Now, we chose X, the equal angle X, to be on this side. What if we had chosen the equal angle X or to be on the other side? Well, we can actually call that equal angle on the other side Y. And so I can take a point Q and move it around until all three of these are equal to Y. And this is Brocard's second point. That's pretty amazing. Yes, this point is also unique. Very amazing. And the relationship between these two are pretty mysterious and interesting. Okay, I did a huge amount of work for this video, so it's not fair if you get off the hook from doing any work, so I'm going to give you an exercise to do now. And that is, you find the second Brocard angle y and tell me the following. Is y the same angle as x? That's an interesting question, no? Well, you have all the techniques necessary to find the same kind of geometrical formula for Brocard angle y. You have everything you need here, and you go ahead and find y. Well, as always, like, comment, and subscribe. Let me know what you think of Brocard's points. And if you really like this vid, well, send me a super thanks. And I will see you next time with more really cool late night mathematics. This has been your host, Ted Z.